hear me well? I don't see you with these lights. Thanks a lot, Frank, for this generous introduction. And thank you guys. I'm thinking of Frederic and Frank, the organizers, for putting together this fantastic event in this fantastic place. And I had never been to Saint-Malo before, so I went. It was, I think, with Eva that a few years ago we had this ANR, and then we went to Rennes several times, but didn't stop there. We never made it all the way to Saint-Malo. But I think I will be coming here for vacation because this is truly a great place. So there is this, and I also wanted to have a few words about Paulette Lieberman because I think it's a very good initiative that we dedicated this conference to her. So I belong to this generation who met her when, well, she was obviously retired. She had a certain age. She was very inquisitive, so as Eva pointed out several times. And I think that the first time I met her, it was in 1997 in one of these séminaires Sud-Rhodaniens organized by Nicole Desaulnieux, I remember. And that's the first time I met also Charles-Michel Marle, so the other half of the book. And so in any case, it's not only for female colleagues. I mean, for male colleagues like myself, it was also very influential because, you see, I was into geometric mechanics full-time. And anyway, they helped young people a lot, not only with demanding comments and so on, but also being encouraging and showing us how important the subject was and still is. So in any case, I think that it's very good that we have a thought for her and that, we dedicate this to her memory. Okay, so let me tell you about what the talk is going to be about. So, as I said, I have this past in geometric mechanics system at time t that are perfectly determined by its value at t-1. When it comes to the observations, you need to add memory in order to catch up with the loss of information. Here we go with information again, that represents just going to observations. So, in this respect, I will not have time for this, but in doing this reservoir computing business, we have realized that there are very nice and mathematically interesting connections between this notion of generalized synchronizations that the physicists have been working on for many years, and the ability that we have to learn the dynamics of these observations and using reservoir computing. So we have a recent paper in nonlinearity where we extend basically Takens theorem in order to account for what I just said. So other examples is, well, what you see here. So there are something that you may keep in mind is, nonlinear regressions as they appear in econometrics and in macro predictions. So as soon as you do forecasting, you need to have things like this. So think, for example, of the standard forecasting problem of the GDP of France, right? So if you go to the Banque de France, next to the Louvre, there is an entire floor of people who are dedicating their lives to determine what are the right use that you need to use, how far into the past you need to go, and then they tell the governor every quarter, this is what you are supposed to do, and this is what the GDP at the end of this quarter is going to be, right? So, this could be inflation, this could be financial variables, this could be many other variables that these people take into account. But the functional that ultimately you need to determine is of this form, right? And then the one that is going to be a privileged setup for us is this state space system. So whenever you have a state space system and you happen to have this equistate property, then you end up with a functional of the type that I introduced before. So you see, I know that there are control people here, and but this is not a control talk in the sense that, you see, when you have a state space system like this, well, usually you care about controllability, observability, these kind of things. And here, and then in order to do that, what you do is you fix an initial state, right? And then you care about how many points you can reach with a YT and so on. So in our case, we care about input-output. So I want to determine if I fix a semi-infinite path of the C's with no initial condition, if I will be able to uniquely determine such a thing. That is non-trivial, because it's not trivial that if I fix a semi-infinite sequence here, there will be a unique YT that will satisfy simultaneously these two equations. So that's what we call the equal state property. And in that, when it happens, when it is satisfied, then automatically you have a capital H, we call it functional, and then just by time translation, you get a filter that takes you from sequences to sequences, right? So this is the kind of dynamics that we want to learn. Not only that, and now I'm going to be just purely deterministic, but as I already told you before, you can go stochastic with these things. It's mathematically very different. So this talk that I'm giving to you, you make it stochastic, the kind of tools that you need to apply are very different. So here you're going to see a lot of Stone-Weierstrass, internal approximation, so very classical things. And I'm talking about very classical things, something that is apparent from the examples that I just gave you, is that there is a lot of extremely classical mathematics that we can use in order to tackle the problems that I'm going to be posing, because this talks to systems theory, non-autonomous dynamical systems. These are extremely classical, well-developed topics in mathematics. Right, so I told you what we want to model, but then we are not going to model in this setup everything. We will use an extremely important modeling assumption, which goes back all the way to Volterra and to Wiener, which is this fade-in memory property. So you see, when we were talking about the Banque de France and the GDP forecasting of France, so something which is obvious to any modeler is that if you want to know the GDP of France next quarter, probably the unemployment rate, the inflation rate, and the CAC 40 value this term is much more important than those values in the 20s, for example. So you want a model that takes that into account, right? And that's what Volterra called fade-in memory. A first extremely natural postulate is to suppose that the influence of the input a long time before the given moment gradually fades out. So that's something that most of the models that we use in applications, let's call it like that, satisfy that postulate. The first mathematical characterization of such postulate is due to Steve Boyd and Leon Chua in a paper that they published in 1985, in which they characterized it as a continuity property with respect to a weighted norm. So a weighted norm is you just take a norm, right? And then you just take an strictly decreasing sequence, right? And then you create a new norm. It's a weighted norm. So what I just said amounts to, mathematically, to imposing continuity with respect to these weighted norms, right? And the proof is that whenever you have this kind of continuity, you have the so-called input forgetting property. That means that if you start with, you see, you have two paths that come from minus infinity, right? And then you start feeding to this H that happens to be fade in memory the same input, right? Even though they are coming from totally different paths, at the end, if you keep feeding the same thing, the different path that they had is forgotten, right? And then they end up being closer and closer, right? So this proves that this, mathematically speaking, there is something that this MP and this continuity property do for you, is that on uniformly bounded inputs, they create compactness, but a strong compactness, not weak compactness a la Oglu, okay? And then that, you see, we are going to be doing approximation theorems and things like that. Stone-Weierstrass, it needs compactness, if you remember your calculus, okay? So anyway, so okay, I told you this is learning of dynamic processes. We know what dynamic processes are. I told you what the kind of processes that we're going to be learning are. And is this fade-in memory business. And then, well, if you think of, forget processes, think of functions, right? So in order to learn functions, what do you need? So you need a, if possible, parametric family that happens to be universal. Think of polynomials, Fourier, neural networks, and so on. So we need something like that in this context, right? So I'm not going to say it's the first, but the first one that I will be telling you about is in this paper by Boyd and Chua that I was telling you about. in which they prove that Volterra Volterra series are universal in the sense that they have uniform approximation properties when it comes to these processes, dynamic process that I was telling you about. Volterra, for those of you who never saw it, is just Taylor, okay? And if you don't believe me, look at what happens when you truncate it. If you remember your complex analysis class, when you truncate an analytic function in its power series expansion, you get something like this, right? So this is what happens with these people. So this is just an infinite dimensional extension of Taylor, okay? Here you can truncate on the power of the polynomials that you are using in the expansion, that's what gives you this part, or you can truncate also on how far into the past you go. And then that will come with a sequence that is actually a related sequence to this fade-in memory continuity that I was telling you before. Anyway, so this is very important, and actually it will be a key result that we will need later on. And it gives you some sort of learnability, right? Even for those of you who are not into machine learning, you see, if I give you a U and I have realizations of this input-output relation, and then you want to learn this U out of data, all you need to do is to find for me these G's. And then these G's happen to be a linear functional acting on this polynomial basis. The linearity, if you just use MSC, the L2 norm as or an empirical version of it, in order to do the training, this means that this ends up being just an ordinary least squares problem, right? For which you actually even have bounds, right? So this is true. All I said from the usefulness point of view is not great, because if you have done polynomial regressions, you see that the condition number of the covariance matrix is not good, okay? And then if you want to program a Volterra series, it's complicated because you have all these summonds. Each time that you need to go is not iterative, right? So it's time that you need to go to one time into the future. You need to recompute all these infinite sums or these truncated sums. So anyway, but look at what we achieved, or what these people achieved. So we are able to write down dynamics on a basis, polynomials, right? And basis which is independent on the U that we want to use. So you see, if I have another U and I have the same input and output, all I would need to change is these G's, right? So these people, they remain put. So this is what we call a strong universality, because you have this U independence in the learning scheme, and which is going to be very important for the discussion later on. Very good. So this was with learning with Volterra, and then our paradigm is going to be state space systems, alias recurrent neural networks, right? So this is what we want to use to learn. And here, this is I want to make a connection with something extremely classical and dear for some of the people in the audience, which is the realizability problem, right? So if I give you an input-output system, give to me a state space system that does it for you. So this is obviously not uniquely defined, because there are these system automorphisms and so on. And it's in general a very difficult problem, okay? So here we change the optics of it, and then what we will not do is to realize a given filter. We will just approximate it like we do it with neural networks for the finite dimensional case, or with Volterra, right? So the advantages that the state space systems have is that they are easy to code and they are easy to work with, because they are Markovian on the states, right? So this is just a for loop in order to make it run, right? And then you see, when it comes to information processing, you see, the C only happens here. So you could go for multitasking. You could just have different H's for different tasks. Going back to the GDP of France example, suppose that I want not the GDP of France next quarter, I want it in 1 year and in 3 years, right? So I could process the information, the inputs, all this available information that I have in the C's once, and then I could train different H's for each of the tasks that I am interested in. It would be great if that could be done. A different story is if it can be done, right? And that's something that I will prove for you, at least in one specific context. So, right. So something that we proved with Ludmila Grigorieva, who is sitting here, already a few years ago, is something which is relatively simple. So is that actually state space systems that have this ESP property, they happen to be universal in that sense, okay? So, but actually universality in this, for ESP state space systems is no big deal. Actually, you need very little in order to have universality. So actually you can just achieve it with linear people. So if you give me a linear filter, a linear state space system, with a universal family for the readouts, so you use as readouts a concept class that happens to be universal in the continuous category for maps that go from the x to the y's, right? These people are going to be universal, uniform approximation holds, and actually these A's, they don't even need to be full. They could be just diagonal or nilpotent, right? So what I'm trying to say is that universality is easy here in this context. What is not easy is something that is going to be desirable for us. Because I told you, look, here we are into learning with, if possible, yeah, let's use the language of time series. We are going to learn with parsimonious families, so I don't want to have many parameters. And then I want that the training is easy, right? Look, if I use this, I will need to find the A and the C. These state spaces, they could be very big if you want to achieve good approximation properties. And then this could be a huge deep neural network, right? So what I want, and this is my first definition of reservoir computing that I am giving to you now and that I will repeat a couple of times more, is what I want ultimately is that I achieve good approximation properties with something that is going to be randomly generated here, and with something that here is very simple, for example, linear, right? So this I just generated, I do whatever I need to do with the input, and then I will just train a linear layout, which comes down to basically running a linear regression. So I want to learn highly nonlinear things with just computing a linear regression. And all the nonlinearity will be hidden in this part, and then here it will be only linear. So I have to do something else because this is clearly linear, right? No matter what you do. So, and then I need to prove to you that this is possible, because it's very nice to want something, but that doesn't mean that you are going to have it. So, so this is what we did with two families of systems like this. So the first one is a generalization that, again, with Ludmila, we took care of, and that we got the inspiration from relatively old classical papers from Flies and Normand Sirot. So these are all these great names in systems theory in France. So these people, they had something very similar to this thing that I'm showing to you, in which what you use for a state equation is a polynomial on the inputs with matrix coefficients. So you see before, here you have just a matrix times xt minus 1. So what you have now is this polynomial on the inputs with matrix coefficients, and then the same story here. If you use this type of a state equation, actually you can achieve universality with only linear readouts, okay? So that's one fact. And then the other, so these people are universal. And then the other family is something which was already suspected to be universal for a long time. So there are these equistate networks. So the history of reservoir computing is coming from different places. One is the bucket of water, but the other one is these equistate networks that were actually introduced in a PhD thesis in the 90s by a student in ETH in Zurich. And then they were rediscovered by basically Jäger and Haas in a paper that I will show you in a minute. And these are, if you want, the recurrent neural network version of neural networks, because you see the state equation is basically a neural network without the linear readout, right? And but the readout is linear, you see? So, so that's what makes the training extremely simple. So yeah, the universality of these people, it was anticipated because they behave extremely well. But somehow the universality had not been proved, and it's something that we did in a couple of papers, and that we extended to the reservoir computing setup, because this is still not reservoir computing. You see these A, these C's, and these zeta, we have to train them too. So what we proved more recently is that actually just by randomly generating this A, C, and zeta, you still can achieve this uniform approximation property. So, right, so again, this I already said it, we are not solving the realization problem, okay? So we are showing that you can approximate any fading memory input output with something that looks like, which is a state space realization, but this is not an identity, it's just an approximation. The proofs, they go depending, for example, in this Flies-Normand-Sirot state affine systems that I was telling you about, these Stone-Weierstrass basically. For instance, it's more complicated. That's why it took a while to get the result. And then, as I said before, if you want the stochastic extensions for those results in which the input and the output are stochastic, it's a different story, so the mathematics are different. But it follows the pattern that was done, I'm thinking of the classical Hornig papers in neural networks, the journal. So there what you do is you see, when you do a Stone-Weierstrass, I told you that you need compactness. So compactness is achieved by restricting to uniformly bounded inputs. If you have stochastic inputs, you cannot do that, because if you have something which is not compactly supported, like Gaussians, so then you cannot impose that, right? So the solution for that is that you prove universality. Let me avoid this because it would take long to explain. You do it with LP, right? So you define an LP norm using the law of the input, right? And it's with respect to that you prove universality. So anyway, so this is, if you want, some collections of universal setups. But now let me focus on the reservoir computing business. So now I'm going to tell you exactly what I want. So I give you a bunch of state space systems that have these universality properties. But now what I want, so sorry. So now what I want, so this is what I told you that I wanted to do. And now I'm going to do it out of, well, this is the data that we have. And then the main difference with respect to what I told you is that now I'm going to impose randomly generated state equations. I want these matrices, for example, in the equistate networks to be randomly generated. And I want the readout to be purely linear, so that training is cheap. And well, for the time being, we are doing everything in a supervised framework. And this is what I will define as reservoir computing, okay? There is a huge part of the community mainly made out of physicists, photonics, electronics, optoelectronics people, for which reservoir computing means something else. And these are actually the people who invented or who put the phenomenon out there, because of what I'm going to tell you, looking at this picture. You see, and this is actually how, we got these people here in the front row, when we were, all of us back in Besançon, Franche-Comté. So we had this physicist in this femto lab. It's the most important lab in the region. So these people, Laurent Larger is still the director of this place, and then he came to us and he said, well, you are mathematicians, we came up with this experiment. Actually, what we have is something that generates this time delay differential equation. We just sample it, we train this readout, and then all of a sudden we can do, I don't know, digit image recognition and all these basically machine learning applications. What is going on here? So anyway, so with Stéphane Chrétien, Ludmila Grigorieva, and myself, we started looking into it. And you see, all the papers that we see in there, they were physics papers. So these people, they were using this setup and many others in order to conduct this reservoir computing, as they called it, and very successfully in applications, but for which there was no mathematical theory, right? So that took us a while. So look at the dates. So it has taken us 10 years, basically, to understand and to put things in a context that, for which we can prove theorems, right? So our goal was to be able to prove theorems out of this. And I'm happy to report that we succeeded to some extent, even though, as I said, there are many things to be done. But in any case, we were part of this community because it's very interesting. You see, the fact that you can do machine learning with setups like this, especially if they are purely optics, makes them extremely fast. And this is what these people are after. So they don't want to use standard computers. They want to use dedicated hardware to simulate the equations that create this state space in which your dynamics is being embedded, out of which, out of a linear regression, you get the information that you want. This is the idea that these people have. And they are extremely successful at it. So this was the beginning. This was, for their standards, slow. Then, well, there is Daniel Brunner, who came also to Besançon. He came up with these purely optic setups. They are somewhat limited. This was a bit like, you know, quantum computing now. So all these materials, some of them, they are passive. It's all very linear, like all optics is, unless you have active materials. And anyway, then I went to Switzerland. I teamed up with IBM Rougelicon, and then we kept working on these things. But so for me, these physicists, they have always been an extremely important source of inspiration, because they impose a lot of constraints, but at least they guide us on what is the kind of theorems and hypotheses that we should be willing to live with. So anyway, before I get into more theorems or into an explanation of this phenomenon, let me tell you one specific setup where this thing is used. And because for the rest of the talk, what I will do is now I will give you a couple of examples of applications, very simple, and then I will give you an explanation of this reservoir computing phenomenon using a geometric argument, right? There are others that we have, but anyway, but let me tell you, for example, how you would use one of these systems in order to forecast or to path continue a dynamical system. So what you do, what you are given as data is a bunch of observations of your dynamical system, right? Of finite sample, right? So then you run them through the state equation, very simple, and then you get a temporal trace of states. So usually this is dimension little d is, yeah, if it is, I don't know, one component of Lorentz or whatever dynamical system you want. Usually this is typically much, much higher. So the dimensions here are in the thousands, right? And this is what we call the listening phase. So it's out of a time, out of a temporal trace of observations, you get a temporal trace of states. And then based on that, you train a readout out of this concept class, which, as I told you before, in the reservoir computing setup, this concept class is going to be, or this class of functions is going to be just linear functions that minimize, for example, this is purely deterministic, is a deterministic system, are going to minimize this MSC. And then once you have this H, what you do is you close the loop, because what you train this is you want to obtain out of this H and the state at time t, the value of the observation at time t plus 1. So that's why you minimize this mean square thing. Once you have it, you can construct out of it an autonomous dynamical system, which is going to play the role of a proxy of the data generating process that you used, that created the data that you use at training, okay? So it could not be simpler than this. And actually, this is something that has been done forever, using, for example, embeddology and all these tokens business. And so the idea is not new. What is new is that you don't use delay embeddings through tokens. What you use is this state space setup. Even though one of the observations that you will see in some of our papers, if you go to any of our web pages, is that what is making this possible is that what we are creating with this F and this H is something that I mentioned before, is these generalized synchronizations that physicists introduced a long time ago. The delay embedding of tokens is a particular example of it. But there is no reason why it should be just the delay embedding. There are many other generalized synchronizations that you could have. And when equal-state networks or reservoir computing is being successful is because this generalized synchronization exists. And it has the same properties that Takens embedding has. Namely, it is injective, it is an embedding, right? So it is invertible. Something that we were able to prove in this recent nonlinearity paper that I told you, where we did it for linear systems that generalize Takens. But for the nonlinear case, for example, for ESNs, is an open problem. So which I talk about to everybody who comes to my office. So anyway, with these people here, we have been trying to do it for like 3-4 years minimum. Somehow we didn't manage it. So there is a lot of differential topology that goes with it, like in the case of Takens, by the way. So anyway, so let me show to you just pictures of so this is the classical or the famous Jäger paper that started this reservoir computing business. So they predicted, or their path continued, the solutions of this Mackey-Glass time delay differential equation very successfully, or in any case, probably you don't see it there. But yeah, accuracy is improved by a factor of 2,400 over previous techniques. Previous techniques is basically Takens, okay? So anyways, so yeah, here you see that they go up to 3 Lyapunov times, I think, that they go. And then more recently, and I'm a big fan of these results, so there is Ed Ott in Maryland with a bunch of brilliant young people, and they have, well, basically use these techniques to forecast yeah, quite a bit of interesting equations. The first one they did that put them in the map when it comes to this. I mean, Ott, he's been together in the map, but when it comes to reservoir computing, the first success story was this Kuramoto-Shivasinski. And then we have this interest group at the Alan Turing, and then, well, he gave this fantastic talk a few months ago. Well, they are applying it now to weather modeling, climate, and then they have these very interesting hybrid schemes, for which, by the way, we have no theory, so we don't have guarantees for those. But in any case, so the physicists, they are truly a source of inspiration, and a source of problems for phenomena to be explained, right? So. Yeah, it's time that I go to one of their talks. Yeah, I have these mixed feelings of anticipation, and you never know what is going to happen. So, right, so here you have a picture that this is coming from them, right? So this is not us, this is Kuramoto-Shivasinski. So what you see here is the actual solution, actual meaning, I don't know, finite elements or some very expensive numerical method. And this is basically what you get out of data, right, by running a linear regression, right? So, you see, in order to reconstruct this picture, it's not only that this is numerically cheap, because it is just a linear regression. You don't even need to know the equation, you see? So you truly learn the dynamics. And in this case, well, this is one minus the other. So you see that up to 7 Lyapunov times, yeah, there is basically no error. And of course, these are chaotic equations. There is a positive top Lyapunov exponent. So at some point, you know that they will diverge. However, what is important, that this is what I keep repeating in every single talk I give, is that even when there is a divergence there is an error between the actual solution and the proxy, this still looks like a solution of the original system. So this tells you that the dynamics has been learned, even though for natural causes, you will commit an error, okay? So this I find very interesting and very motivating, because this is for Lyapunov spectra, things of that sort. And then let me conclude with, you see, I gave you universality results for state space systems. What about reservoir computing? I didn't do my job yet. How is it possible that with these randomly generated state equations, I am able to uniformly approximate these fading memory dynamics? So I could go 2 ways. So the ones that has been the most costly is to just follow the usual machine learning path, right? So to prove basically approximation and estimation bounds. That we did, right? So in a very barren type of arguments, that the last one, when it comes to approximation that appeared in the Annals of Applied Probability earlier this year, right? And but in any case, that's if you want more traditional. But since we are in GSI, I wanted to tell you about this geometric argument, which is related to this Volterra that you saw in the beginning. So, so this is what I will use as a quick explanation, even though it requires certain technicalities. So the first one is, so what I'm going to do is two things. So the first one is I will create a state space representation. This time it will be a realization of the truncated Volterra filter. So, so Volterra admits a state space representation, right? When you truncate, it's going to be a finite dimensional representation whose state space will be this tensor space, whose dimensions may be crazy, right? Because this is a tensor space. This is D is the dimension of the input, so this could be very big, right? This is admittedly suboptimal when it comes to numerics. But anyway, if you want that, this is how it goes. So there is this state equation whose solution is actually a bunch of polynomials that contains all the monomials in the Volterra basis up to order P and lag into the path L, okay? So this is all this thing is doing. And that's how I am able to represent Volterra as a state space system. If you take into account what I just said, I will go back to this, you can prove this, right? You can prove that actually any causal time invariant fading memory filter can be written as a linear readout of the solution of these funny state space systems on this tensor algebra, right? For those of you who have done signatures having to do with the solutions of controlled differential equations, this is very similar to the signature process. So the difference is that the signature process is defined on continuous time. You write it, there the state space is going to be basically the free algebra generated by as many generators as the dimension of the input. Then instead of something like, instead of having basically monomials, you're going to have these iterated integrals, right? But the important thing is that you are able to write this, the filter that you are interested in, or you are able to approximate it as a linear readout of something that is admittedly potentially very high dimensional, right? But it doesn't matter. It doesn't matter because now I'm going to go to the dimensional reduction part that will give us this reservoir computing flavor that I was telling you about. Because see, up until now, okay, this is one more twist on Volterra, but there is no reservoir computing here. There is no randomness, right? That happens if you realize that this state space system that I wrote for you in this tensor space is a SAS. It's one of these state space systems a la Fleece Norman 0, okay? But it's huge, dimensional, and it's purely deterministic. So the coefficients are given to you, right? Once you fix them, once you fix the system. Where is the randomness here? And how to reduce dimensions. So, sorry for all this. So this is what I just said. One tool of choice is this Johnson-Lindenstrauss lemma, right? For those of you who never saw this before, what this Johnson-Lindenstrauss lemma tells you is that if you are in a huge, potentially huge dimensional Hilbert space, this is a Hilbert thing, you choose a bunch of points, right? You randomly project this Hilbert space into something smaller dimensional, and with high probability and epsilon, I will talk about this epsilon in a minute, that have to do with the drop in dimension and how many points you have, in the projected space, you will not have an isometry, so the distance will not be preserved, but it will be approximately preserved, right? So this is for those of you who have done some dimension reduction in machine learning. This is very much used. The quality of the dimension reduction is not great, actually. So if you do numbers with these epsilons and these drops in dimensions and so on, it's not really great. And But anyway, this is what I will use as a technique. You see, now going back to what I showed to you in this theorem, we have this huge dimensional tensor product state space, right? So what I'm going to do is I'm going to use basically this Johnson-Lindenstrauss in order to dimension reduce it, right? So the punchline is, and I spare you the details, is that what you obtain at the end is a reservoir system. But this time it's going to be an honest-to-God reservoir system. So it's going to be a state-affine system in which the AIs and the Bs are randomly generated. And then I even tell you, and this comes from Johnson-Lindenstrauss, what is the law that you need to use in order to generate the entries of this matrix coefficients, okay? So this is, if you want, a geometric interpretation or explanation of this fact that I told you before, that just by using randomly generated, in this particular case, state-affine systems, and with linear readouts, you are able to uniformly approximate this fade-in memory dynamics. So, so the punchline is, and I wrote it here, so what is the upshot? So randomly generated SAS have universal approximation properties because they are the random projection of a high. Actually, if you don't truncate, it's going to be infinite dimensional state space system with a strongly universal approximation properties. So the infinite dimensional is something that we truly can do and we truly can handle. So in a more recent preprint, you see, we answered the question, what if we don't want to truncate, right? In that case, we are going to have, it's not going to be a tensor space, it's going to be a tensor algebra, so it's going to be infinite dimensional. And then you can kernelize. So what you do is you have this state space equation. It's going to have a unique solution. You will have this equal-state property. And then you can use this solution map as the feature map in the construction of a kernel, right? And once you have the kernel, if you are given data, all you need to do is to use the representer theorem in order to train for the given dynamics. You don't lose linearity. It's not going to be a regression. It's going to be, well, it's going to be a Gramian regression, what you will need to solve. But the beauty of that is that, you know, this state space structure that we have gets inherited by the kernel itself. So there is a recursion that was to some extent also known in other contexts in other papers. But in this context, you have this recursion that you can use in order to compute the kernel very efficiently. And that amounts to, that allows you to use this infinite dimensional situation. So I see that Frank is moving already. Very good. So anyway, this is something that I wanted to tell you just to give you an idea of one particular situation where this could work. Look, I will not go through all this, but if you want to take some, a take-home idea here is that you see, we have dedicated a lot of time to prove that reservoir computing, which is actually something that 10 years ago was only just known to physicists. It was used in the lab. They had all these benchmarks and so on. So we made it into a provable, reliable concept class, which is, if you want, as honorable as other families that you have in the machine learning literature. So if you want to go for the more traditional machine learning explanations of the phenomenon, you have it there. So then, as I said, you can also do these things stochastic. I didn't touch on that because it becomes very technical very quickly. So I didn't think that it was so interesting. And then there is this relation with kernel methods that I told you about. So you have it there. And anyway, and then there is this link that we collectively plan to explore further, is the relation with non-autonomous dynamical systems. So ultimately, this thing is a non-autonomous dynamical system for which there is a huge literature, even though it is a pretty recent literature, you see. So even the notion of attractor, here, you have these pullback attractors. That's actually what these reservoir computing systems are exhibiting. And but in any case, we need to work more to understand that better, because I think that there is a gold mine. Right, memory forecasting capacities. Yeah. Anyway, so I will post these slides, or I will give them to Frédéric and Frank, and then you can look at all this. And anyway, when it comes to open problems, let me mention at least just this, because you see, we are in one of the temples of geometric mechanics and geometric methods for dynamics and so on. There is there is this argument that I use to prove that reservoir computing and so on is working and so on using geometry, but there is no structure in any of these systems that I told you about. And in this community, we are very fond of structure, right? It could be something coming from physics or from control, right? Or it could be coming from symmetries, right? Like as we saw in yesterday's presentations. So this is something that we collectively should develop. I am very much interested in it for, if you want, personal reasons, because I have this past history on the subject. And then something which is potentially very interesting is, you see, there are these experiments and this dedicated hardware that I showed to you having to do with optoelectronic systems. These days, what you want to do is quantum systems, right? So I teamed up with these people in IFISC. So Rodrigo, he came to, he's a student from IFISC, is this Complex Systems Institute in Palma, in Mallorca. And then, anyway, so we are extending what you saw to quantum systems, in which the state space is going to be basically density matrices, right? Like you do in a standard quantum mechanics. Very good. So I will stop this. I need to say two things. So the first one, I wanted to thank all my collaborators over the years. So I have to start with my masters, so Jerry Martin and Tudor Rachu, who was one of your keynote speakers a few years ago. And then, of course, there is Ludmila and Lucas, with whom we have written tons of papers. And so this is our team in Singapore. So we were all in an excursion a few months ago. And if you want to know that it is Singapore, all you need to look is at our T-shirts. We are sweating like this place is humid. I mean, it's... But in any case, and then some of them are here. So let me, so Ludmila is here. So there is Dai-Ying, who is here, who will be giving a talk about these subjects. Stéphane Chrétien, my beloved friend from Besançon, he's also here. Cyrus, he's also here. And Nathael, I think, is there. He is. So I don't see anything from with the lights. So, and then final point, I need to make publicity. So people, we need your help. So I tell you a story for those of you who don't know about it. So 15 years ago, if not more, under the leadership of Manuel de Leon, who is in the back, so we created, with the help of André Lewis and a fantastic panel of editors, this Journal of Geometric Mechanics that you all know. Anyway, this journal does not exist anymore. Well, it does exist, but it's not the same journal, because it was published by Ames. Ames, I don't know what happened in there, but they wanted us to be basically a predatory journal, or at least a journal that was not compatible with our values. So in any case, it was great. We made a revolution. We just all resigned. And then with the help of World Scientific, so this is becoming more Singaporean now, we created this Geometric Mechanics Journal. It's the same editorial board with a few additions, especially young people who will help us with some of these topics that you are seeing here. So we are opening also to learning and to more modern topics, apart from the traditional ones that the journal used to have. So in any case, it was great to make the revolution, but now we have to make it happen. So what I'm trying to say is that, you see, after 15 years, we had this comfortable 1 year, 2 year backlog. It was every day with Manuel and with Andrew, we shared our emails. But now we don't have that anymore, because Ames, they kept everything. So we need submissions, and what we promise you is that we will treat them very well. We will be very careful. We will have the best of our attentions, among other things, because we truly need you. I mean, we need to have a number in March 2024, so we count on your support. Okay, and I stop here. Thank you very much.
Thank you very much, Juan-Pablo, for the very inspiring talk. So I think I don't want to eat too much of the coffee break, so I propose 1 or 2 questions, and maybe during the coffee break, other question could be addressed to Juan-Pablo. So is there some questions? Can I take? Everyone wants to have a coffee, right? So okay.
No, I have a question. The method of reduction could be related that, for example, for Poincaré unbending method, hyperbolic embedding is the same kind of reduction, or?
Not really, or at least not obviously. You see, we are to the point in which all we know is that under very constraining conditions, these proxies that we construct using reservoir computers, they exhibit the same normally hyperbolic attractors than the original systems. Not the same, they're obviously topologically conjugate. So up to topological conjugacy, you have that the proxy is going to have a normally hyperbolic attractor that is like this related with the original system. But again, there are all these hypotheses, and some of those hypotheses in this embeddology part of literature, they prove that are satisfied. So if you go, for example, to tokens, so you know, injectivity and embedding is something that you need to prove with very sophisticated topological, differential topological developments. So here it should be the same, but somehow it's very difficult. We're at that level. So if we now try to go to dimension reduction and reduction, that's I wouldn't know how to put Poincaré bendix on there. Do you see what I mean? So, but this is a very good point. It's a very good question. Yeah. Unfortunately, I have no answer for it.
Another question about the independence of the coordinate system, because you should have a dynamic that will, so the speed of the dynamic should not change if you change the coordinate system.
That is part, well, first of all, most of what you saw in here is in discrete time, so those considerations in discrete time, they become very complicated because they appear as algebraic constraints in the setup, and yeah, there is not as beautiful and as neat as we are used to in the continuous time setup. So something that, well, with our students here, we tend to do is to go first to the continuous time setup and then just to basically find a discretization setup that doesn't spoil this structure but this is part of this structure that I was talking about. So ultimately, there is an invariance property that we should be able to impose. And in all the models that you saw in here, for which we work very hard in order to find guarantees and all these nice properties that you have in machine learning, well, even though we manage in that setup, if you impose additional structure, it's going to be very complicated. So no, we are not there yet. We are not there yet.
Okay, so I propose that I propose to keep the discussion live during the coffee break, and let's thank the speaker again.